Okay, so we are going to combine our quiz, not quiz, semester-long design problem and talk about how we would uh, design the actual nozzles that produce the thrust for our space tower. So we've already learned quite a bit about how to design this tower. We know that we cannot put a very large pump down at the bottom of our tower and expect to just push the water up with enough pressure that it can actually produce the thrust we need. That requires very thick walls, which are very heavy, which requires more lift. Then it's just a runaway problem, right? So the reality is that we want to have very thin walls here with occasional booster pumps that keep the pressure quite low inside of this main tube that is going up. And then we'll siphon off a little bit of the water for each pump that produces thrust, and we'll have a high pressure pump here that then creates a very large delta P and creates as much thrust as we can, because we want as much exit velocity as we can get. So I think I told you about the pump I found, which was a delta P of 4 times 10 to the 8 pascals with a Q max of 4.1 times 10 to the negative third meters cubed per second. And we want to know what is the thrust produced by our nozzle we designed. So we designed a nozzle that had, using conservation of mass, had an area exit of 3.2 times 10 to the negative 6 meters squared, which would, if we remember right, was like a 2 millimeter diameter nozzle. And it had a exit velocity of 1,265 meters per second. And we found our exit velocity using Bernoulli's, and we used conservation of mass to find our exit area. Now, an important thing to know is that the mass of this pump is equal to 170 kilograms, which is heavy, right? That is very heavy. We're talking, 350 pounds, 400 pounds for a pump. Let's see now if this produces some net thrust. All right. So again, we always ask ourselves, we're trying to figure out what is the thrust produced. What model do we use? Well, we need something that can handle forces and pressures and velocities and areas, and the only thing we have to do that is conservation of linear momentum. So we're going to write down our conservation of linear momentum equation. Sum of our forces is equal to dt integral over of rho vxyz dv plus integral, again that's over a control volume of control surface of rho vxyz times w dot n hat dA. So step one, always draw a control volume, right? And our coordinate systems. Draw CV and coordinate systems. So we're going to do that. I'm going to draw my CV around my pump. And then come here across the bottom and cut across the jet. So our CV is going to cut across the pipe at the top of the pump, and it's going to cut across the jet at the bottom, and everywhere else it's going to be in the air. And we're going to put, this isn't moving, so we're going to just put our coordinate system right next to it. X, Y, Z coming out of the page. And now we have to write our forces on our control volume. So here we have some pressure acting inward on our control volume due to the pipe. So we're going to call that P times A1. We'll call this 1, entrance 1. And we've cut through pipe, right? And there are going to be internal stresses in the pipe that we cut through. So there will be stresses on our control volume due to the pipe, and we're going to call those F, the sum of all those stresses times the area, F pipe. And it turns out that F pipe is what is holding this pump in place. So this will be equal and opposite too hard. I don't know if you guys can hear that, but the garbage truck is honking at my child on our front porch. So the force of this pipe is acting on our control volume is holding it in place, so it will be equal and opposite to our thrust. Okay, great. So step 2, we've picked a direction. We didn't really realize it. Oh, we forgot one more thing, which is to write mg here for on the pipe. So we've picked a direction, which is F pipe times pressure time, and our pressure and area and our mg are all in the y direction. So we're going to pick the y direction, obviously. So we're going to write down our equation here, equation 1. We have negative P1 times A1. And remember, it's negative because pressure always acts inward on a control volume, so it's going to be acting down. Plus F pipe. We always draw these forces we don't know in the positive direction, and then whatever sign they come out is the direction that they're actually in. Then we subtract M pump times G. We're going to assume that the mass of everything else is small compared to the mass of the pump. And this is all going to be equal to d dt, the integral over control volume of rho Vy dV, plus integral over control surface of rho Vy W dot n hat dA. And we have to make some assumptions. So let's make some assumptions. We're going to assume steady state, which we can assume because nothing is changing with time, right? We're assuming this pump is just chugging along, producing a crazy amount of thrust. B is going to be density is equal to a constant. C, uniform flow. And I think that's all we can assume right now. So let's assume D, gauge pressure. Awesome. So because of steady state A, this is 0. And because we've assumed uniform flow and rho is equal to a constant, this becomes a summation. Our second integral becomes a summation of all the entrances and exits. So let's simplify and solve. Step 3. Simplify and solve, and in this case we have the thing we're solving for, which is F pipe, is equal to our first entrance. So we're going to call the top one 1, a bottom one 2. So our top one, we have a rho water times a V1, which is negative because it's going in the negative direction. And we have a V1, which is also negative for our W dot n hat. Remember, this first one is for our Vy, and our second one is our W dot n hat. It's also a negative V1 because it's entering perpendicular to our control volume, and it's entering, so it's negative. And then we have an A1. And so this ends up being equal to rho V1 squared A1. And that's our first entrance. Then we also have a second exit now, and we have a rho there too. We have a V exit, which is also negative because it's going in the negative direction. We have a positive V exit for our dot product. Our W dot n hat again is leaving perpendicular, so it is a positive or negative 1 times our velocity, and it is leaving, so it's going to be positive. And then we multiply by an A exit. Excellent. And then we add our mg over here, and mass times our mass of our pump times gravity, and then we also add in our P1 times A1. And now let's go through and look what we know and we don't know. So we know rho, we know V1. Well, actually we don't. We don't know V1. Sorry. We don't know A1 either. We know VE, our exit velocity. We know AE, which is our exit area. We know the mass of our pump, we know gravity, we don't know P1, and we don't know A1. So we're going to make a few assumptions here. Let's do this, right? We're going to assume that by design, remember I talked about this, we want the velocities to be and pressures to be low in our main pipe. So by design, V1 is much, much smaller than V2. Because the whole point of the pump is to add a tremendous amount of kinetic energy to this fluid to produce our thrust. So we can say that this is approximately equal to 0, especially compared to this component here, rho VE squared AE. And then we can also similarly assume that the pressure inside of this main trunk, if you will, is low. So we're going to say this is approximately equal to 0. By design, again, DEF, P1 is approximately equal to 0, at least compared to the other pressures that we're handling here, right? So in this case, we say now can solve for F pipe is equal to negative rho AE squared, VE squared times AE plus M pump times G, which if we plug in our information, we see is equal to negative 1,000 kilograms per meter cubed times 1230 meters per second squared times 3.2 times 10 to the negative 6th meters cubed plus 9.8 meters per second squared times 170 kilograms. So you can see that the thrust produced by our pump is equal to the density times the velocity squared times our area. So if we can increase our velocity, that's the best thing we can do because any increase we get is squared, right? So that is excellent. And we subtract the weight of our pipe. So if we find our number, F pipe is equal to negative 3 kilonewtons. So our thrust is equal to, remember it's equal and opposite to that because the pipe is holding it in place, and so it's a reactionary force. So our thrust is a positive 3 kilonewtons, which is exactly what we hoped for. Our pump and nozzle combined can lift about 300 kilograms or 600 pounds. So is that enough to work with? Can this thruster lift its weight and more? And actually, yeah, it can, right? We've included the weight of the pump in our calculations. We did not include the weight of all the pipes and stuff like that, but certainly we can produce pipes and nozzles that weigh less than 300 kilograms. So this can lift more than its own weight, which means that potentially we could build this tower. This tower is feasible, right? This is great. What qualities of a pump do we want? So we're going to actually kind of lean into our dimensional analysis knowledge that we have now. We want to maximize Qmax times the square root of delta P times 2 over rho. And the reason we want to maximize this quantity is sorry, I didn't mean to write an A there. This comes from Bernoulli's on the this right term here, square root of delta P times 2 over rho. This comes from Bernoulli's, and this is our Vy. This is our exit velocity, or we could also say V exit. And our flow rate is our maximum flow rate that our pump gives us, right? So we want to maximize our the Q times this quantity here. And we want to minimize. So this is not quite our thrust. Our thrust, if we multiply it by density. So this is equal to our thrust. So we want to maximize our thrust. That comes from this, basically. And we want to minimize the weight of our pump. So we want to minimize M pump times G. So both of these are equal to a force. This is our weight. And we have a maximizing our thrust. And we want to maximize the one and minimize the other. So we can define a non-dimensional number. I'm going to just give it the initial, the Sn. We'll call it Sn. I don't know why. Possibly because it's every person's dream to have a non-dimensional number named after them. And we're going to write it out as rho times Q max of our pump times the square root of delta P times 2 over rho divided by mass of the pump times G. This we want to maximize. If we can maximize this quantity, we can maximize the thrust for our space tower. So if we rewrite this, though, so we don't have rho showing up twice, this is actually Q max. And we can leave out the square root of 2 if we want. We can leave it in there. It really doesn't matter since we're trying to maximize this. So let's take it out so this looks more like a dimensionless number, sorry. And put the square root of delta P times rho over M pump times G. And the higher this is, the better our pump will be for our space tower. We want to go up. Maximize this to go up. All right, the next problem I will record is the hardest problem I can possibly think of for conservation of linear momentum, and we will work through it together. Oh, one last thing. If you're out there listening and bored and have something to do, try to find pumps that maximize this value, right? You can plug in the values that we have for the pump that we used in our example, and then try to beat that value.